Okay, so I'm super excited to be kicking off the care reading group, be talking about the statistical structure of identifiable generative models. My affiliations are I'm a PhD student in the statistics department at UBC, supervised by Ben Blum-Reddy. And I'm also a machine learning research intern, currently still at Valence Labs, supervised by Jason. Um, so my talk will act sort of like as a tutorial, loosely based on my research, sort of on the broad statistical and probabilistic structure of all this research happening in identifiable generative models. I think stepping back like this brings a lot of intuition to the problem, and there's a lot of nice structure. And my hope is that it'll be useful for future speakers and the audience going forward. So the outline is as follows. First, I'll introduce statistical modeling as a framework and define identifiability from the statistical perspective precisely and explain its importance. Then in the second part, I'll frame rather general class of generative models as statistical models and also representation learning in these models as statistical inference. And then using that framework, I'll describe the identifiability problem, formally connect it with latent variable indeterminacy, and show general characterization results, what Jason was talking about with the intersection. And then finally, I'll just talk a little bit about strong identifiability, its different definitions, and actually some models that can obtain what I'll call statistical strong identifiability. Okay, so I'll just get right into it. And this is going to be a review for a lot of people just to get everyone on the same page. Statistical models mathematically are just index sets of distributions, here noted as curly p theta, defined on a common space of observations. For example, the family of all Bernoulli distributions with some probability p. This big theta is referred to as the parameter space, and here this would be the closed interval 0, 1, but also sort of highlighting sort of how arbitrary the model is. You could sort of pick any non-empty subset of the interval as well to be the parameter space, and it would define a different model. And then inference, statistical inference is the inverse problem of statistical modeling, which says, given observations, can we deduce which member of the parameter space under the model most likely generated the observations? And in this case, if we flip a fair coin enough times, we'll eventually see a fair split, which lets us conclude that p equals 0.5 likely generated data, and we'll conclude that the coin we're flipping is fair. So identifiability refers to the uniqueness of the inference solution, sort of in the absence of statistical uncertainty. That is, as we approach infinitely many samples. In this case, we'll collect the information contained within these infinitely many samples just as the data distribution, Bernoulli 0.5, and so we sort of can forget about the data. And then identifiability is when, given the data generating distribution, so given this Bernoulli 0.5, there's a unique point in the parameter space of your model corresponding to this distribution. Here's an example of the same data, but with a different model that's no longer identifiable. Say I model my coin flips as the summary of two underlying latent coin flips. If both are tails, then the observed coin is tails. Otherwise, the observed coin is heads. I'm going to model this using the maximum of two Bernoullis with possibly different probabilities. And the observed distribution under this model is going to be this Bernoulli with probability 1 minus the product of 1 minus each probability. And then with sort of our observations from the previous slide, we'll determine that 1 minus this product is going to be 0.5. But this is an underspecified relation for the two individual PIs, and thus this model is unidentifiable, even though the data distribution hasn't changed from the previous model. And this is kind of a stupid model that you never actually consider. So under this statistical modeling framework, identifiability is a really simple concept. It's just the injectivity of the map that sends a distribution, that sends a parameter to its distribution within the model. And so in other words, this means that if you have two equal distributions, they shouldn't be implied by different parameter values. As a technical footnote, equal in distribution either means that all probability masses are equal in the Bernoulli case, or just more generally that all set measures are equal, and this can be in a continuous space. There's a there's a relaxed notion of identifiability. It's really straightforward, and we will use extensively in the rest of the talk, and that is of weak or partial or set identifiability, up to the equivalence relation defined by this tilde. These are all different terminologies for the same thing. For example, in the non-identifiable coin flips, knowing that the observation distribution was Bernoulli 0.5 still constrained the parameters to a certain area in the parameter space, but this not necessarily in a useful way, right? So we'll usually reserve the term weak identifiability for admittedly subjectively useful instance of this equivalence relation. And the takeaway from this first section I would like to be is as follows. In plain language, a statistical model is a stochastic theory. Each distribution in the model represents the limit of observable information, and each point in the latent space represents an explanation under the theory. Then identifiability is about the uniqueness of an explanation for the observed phenomenon under this theory. So notice that identifiability then is just a function of the model design, and in this case, the parameter space and the family distribution that it parameterizes. And identifiability is hence about our ability to do inference on the parameter space, which acts as a space of explanations. So really, identifiability is about explainability and explanation. What identifiability is not about is, by definition, it's not about how well we can fit the observed distribution for prediction or sampling. The definition starts with equality and distribution. And I mean, as a really simple example, we can sample from the Bernoulli 0.5 in the non-identifiable model using any equivalent P1, P2 that brings us to this distribution. And so by definition, identifiability is just not about in distribution prediction or sampling. Okay, so now I'll actually get into the generative model side of things, but I'll start with something perhaps a little bit stupid. I want to start the section with what I think is sort of an interesting historical note. Andrew Gelman wrote on his blog in 2009 that a long-standing principle in statistics is that whatever you do, somebody in psychometrics already did it long before. And this could not be more true in the case of what I'm calling here a generative model, which I haven't defined what a generative model is yet, but so Spearman's theory of intelligence, this is Charles Spearman from the Spearman-Rank correlation, or general ability, proposes this common factor model where this latent G, which is supposed to be unique to an individual, determines performance on several different tests. And I think so. Something that's funny is that he was doing correlation heat maps in 1912. So this is the idea here on the left is if the correlation matrix is approximately rank 1, which here, if you look at it closely, it approximately is, then the data must have been generated from a common factor, right? Okay, just for context and to sort of highlight the scientific or social scientific importance of identifiability, under Spearman's theory, each G should uniquely explain each individual's test results. And that would correspond to strong identifiability of the unknown parameter G. For me, this is probably the most clear example. Okay, but there's a problem. Spearman's G was shown, in fact, to be non-identifiable as early as 1928, which puts into question the theory of general ability, at least in its original form. That's probably why it's still hotly debated. It hasn't exactly taken off since then. In its more modern multivariate form, things aren't much better without any restrictions, although I'll say constraints for identifiability in factor models remains an ongoing area of research in psychometrics that I don't know nearly well enough, as well as I should at least. And the reason for this is because Gaussian factor models are well known to be non-identifiable if we parameterize them this way. by this multivariate loading matrix F, which ends up being the covariance of the observations in this matrix product. Then for any orthogonal, or I call them rotation matrices R, the alternative parameter F prime, which is the product of F and R, is again full rank and implies the same covariance for the observations, and so it's non-identifiable. And since the factor loadings in this case directly imply the latent factors, you just sort of try to take a pseudo inverse. This immediately implies an indeterminacy in the underlying factors as well. And here I've sort of loosely defined indeterminacy to be when the factors are not uniquely determined from the data. To get into this connection to generative models, we could write multivariate factor models as a linear Gaussian generative model. The same rotation indeterminacy can just be seen as a Gaussian preserving transformation. So orthogonal matrices preserve Gaussians. And then if you sort of plug that new f times r thing in, then we get the same observational distribution. Something worth noting is that these rotations can actually be shown to be the only possible indeterminacies in this model. And in other words, this model is weakly identifiable up to these rotations. Building on that, I can give my perspective as a statistician on this specific class of generative models. In particular, I've replaced the linear function with a possibly nonlinear thing, but where we still assume that it must be injective, so that's the same as the full rank assumption, mapping to some arbitrary space, say of unstructured data, such as images or sequences. I've also replaced the Gaussian latent distribution with a possibly more flexible and data-driven latent distribution. The noise term can be slightly generalized, but the idea is that it can be deconvolved without changing the underlying distribution. So additive noise is for the most obvious example, or you can just simply do no noise. And this makes a statistical model that is in essence parameterized by the put forward distribution of PZ by the generator F. And if this push forward notation is unfamiliar, it just means the distribution of Z after transforming by F in the data space. And then in this case, specifying a generative model is just simply to pick a class of generators F and a class of distributions PZ, and these are the parameter spaces. With this framework, many popular generative model designs can just be seen as instantiations by varying F and P of Z. For example, nonlinear ICA, PZ are all distributions with independent components. You might want to exclude Gaussians as well. And then the so-called vanilla VAE is where PZ is fixed as the Gaussian, and then F is determined by the decoder architecture. And I kind of see the vanilla VAE, at least, much like a nonlinear factor model. And we'll just recall that identifiability is now a function solely of the parameter spaces, because sort of the structure of the statistical model has been determined. And so the model design just corresponds to the parameter spaces. And then finally, before proceeding to just to finish the setup, I'll just formalize representation learning as inference in these models. So specifically, the representation of X given an inferred generator F can just be obtained simply by inversion, because remember, we assumed injectivity. Then non-identifiability of F directly implies indeterminacy in representation learning, at least as I've defined it, at least as I've defined representation learning using this class of generative models. So it's hence particularly important to control these indeterminacies if we want to do causal representation learning, where we want the representations to be meaningful causal units of the observations. Okay, so now get into the meat bones of the problem. But before getting into anything, I'll just note that I think it'll be useful to have this picture in your head as I'm going through the section. The design of these figures are generously provided by Jason, so they might look familiar to many of you here. So here, the observations are image renderings of these ball objects on a 2D space. The latent Z are exactly what you would hope for them to be, two continuous dimensions corresponding to the location, and then a third discrete dimension for the color. And the generator F is just like this rendering engine. And something to note is that if we observe the latents alongside the images, and the true rendering engine was in our statistical model, then we could, in theory, just recover it by doing supervised learning with infinite data. Okay, so in these more general generative models, it's pretty easy to see that the factor model indeterminacy was actually just a special case of something that can happen more generally. In particular, you can give me any measure preserving transformation A of some P of Z, and assuming that F composed of A is still in my function parameter space or generator parameter space, then I have this really nasty looking identifiability where the representations are distorted by some arbitrary transformation A. And again, this is one of Jason's animations. Imagine if the position of the balls followed a Gaussian distribution, and we observed these samples of the images. Then I could simply rotate the axis without any probabilistic repercussions, and then my latent axes will no longer correspond to the location of the balls. And there's like infinitely many of these, right? And in case, in fact, the problem is even more general. In case if imagine if I had two candidate latent distributions, PZ and PZ prime, then I simply need a mapping A that transforms PZ to PZ prime, which I can then precompose with the generator to obtain this non-identifiability of theta and theta prime. So notice this, the first scenario with the measure preserving or a transformation was a special case of this, where PZ was equal to PZ prime. Okay, so to explain these non-identifiabilities, we should look at what's really going on in this diagram. So let's just think about what happens under the hood if we were to code up the generative process for these images. I'm going to ask for a 2D Gaussian in the latent space to generate my coordinates. How that happens is the pseudo-RNG is going to give me an approximately uniform sample, which then gets transformed via the inverse CDF to a 2D Gaussian. And then this gets rendered to the image on the right. A fundamental theorem of probability says that any random variable in a sufficiently nice space, the standard probability space, can be generated by a deterministic transform of the uniform 0-1 noise. And this is exactly why inverse CDF sampling works. The problem is I can take any other point along the inverse CDF transformation to be the latent space like this. And then this can happen before it becomes the coordinates to my rendering engine. And this would be a completely entangled but sort of equally valid latent space. And then because the overall generative process hasn't changed, my images are equal in distribution, the generator can sort of adapt naturally and pick up what's left over there. And without any constraints on what the latent space looks like, there's nothing to distinguish any particular latent space along this generative process to be the so-called true latent space. More abstractly, we can think about this general mapping from pure noise to observations as the generative process. Indeterminacies arise because of how we can chop up this map. So where does this latent process end, and where does the generative process begin, right? So if this happens, then this sort of thing in between happens to be our indeterminacy. In extreme cases, the latent space can actually just be pure noise. So the whole arrow is just F, or we can just have a trivial generator, and the arrow and the entire arrow is just G, and then we can actually just see the images themselves as latent space. This is something that is totally valid. Just give me a second. I'm just going to ask. Are there any questions? Yes, I completely agree with Simon. Yes, I'm not being super precise in what I'm saying, so it's good. It's good to keep me in check. Okay, sorry. Okay, so before stating the characterization result, I'll just mention briefly that I've been using the terms indeterminacy and identifiability sort of interchangeably. But that they don't necessarily mean the same thing, as identifiability is this particularly defined concept in statistical modeling. So let's for a brief moment define indeterminacy more formally as the existence of this map A between two equivalent representations. I think this is a pretty uncontroversial definition, and using this definition, our framework, the framework that we've built so far is precisely the right one to formalize the connection. In particular, in a generative model, if two parameters imply the same observational distribution, then there must be a transform, in other words, indeterminacy, on the latent space that induces the transformation from theta to theta prime in the parameter spaces. So this lemma sort of formalizes that connection. And so I can just talk about identifiability as the existence of these latent transformations. This equivalence is easiest to see in the factor model. So here, the same rotation R constitutes a latent transformation on the right-hand side, which rotates the axes of the latent space, as well as a precomposition on the generator, with the factor loading matrix, which is a transformation in the parameter space. Okay, now we're ready to state the general identifiability in terms of these indeterminacy transformations. So because A has to satisfy these two things, specifically F prime being F composed of A, and A also transporting PZ to PZ prime, this implies the indeterminacy A has to satisfy the two following conditions. The first is that it has to be formed by pushing and pulling along possible generators as F inverse or as F prime inverse composed of F, and in particular, this is the contribution from the generator part of the parameter space. And for example, linear generators would imply linear indeterminacies. Simultaneously, the contribution from the other side, from the latent distributions, is such that the indeterminacy must transport between possible latent distributions. So for example, if you have Gaussian latents, the transformation must preserve Gaussianity, or if we have independent components, then the transformation cannot introduce dependencies. And these two things together can show that, for example, if you had a linear Gaussian model, so like a factor model, your indeterminacy has to be linear and it has to preserve the standard Gaussian, and therefore has to be a rotation. And just note that this result assumes no specific structure on the generative model, and I think it describes actually the shared structure between a couple of known results. Here's an easy one. A linear ICA excludes Gaussians in the parameter space, and since it's impossible to transport between non-Gaussians with a non-trivial linear transform, then that only leaves permutations and scalings, and so linear ICA is identifiable up to permutation and scalings. I'll just note that in the ICA literature, this is called strong identifiability, but I'll talk a little bit more about that in a second. Additionally, I think this result provides insight on why certain strategies for identifiability have worked so well. In particular, multiple environments or auxiliary conditioning information or latent interventions, whichever one. I mean, these all correspond to a similar thing here, have been extremely successful in reducing indeterminacy. And it essentially boils down to the fact that this thing on the left here has to hold for each environment. And so if we fix the generator across many environments, but vary just the latent distribution, A has to satisfy this property for all the environments, which makes a much stronger constraint on A than if we just had it for a single environment. This makes for a sort of fun result. In the case of multiple but fixed Gaussian environments, it might not be so realistic, but it's fun. And it's very concrete instantiation, so I'm going to talk about it. Specifically, suppose that A is such that it preserves this collection of Gaussians with some fixed covariance. It doesn't have to be the identity. And amongst those, it includes one that is mean zero. Then we actually have that AZ only varies in the linear subspace implied by the orthogonal complement of the span of the non-zero means. So on the right here, we can look at this very concretely. Let's say we have three environments. The first one is mean zero, and then the second and third are these two basis vectors. Then actually the only remaining indeterminacies are on the third dimension, which means that you're actually strongly identified in the first two dimensions, and the third one sort of you can't say anything about. And I'll just note that this is a special case of a general property of exponential families. This is sort of the most simple one that was leveraged, but I don't think it was ever explicitly stated in the nonlinear ICA and identifiable VAE line of work. Okay. Let's stop briefly for questions. If anyone has anything, I'm happy to answer.
You have a
Yes,
question from
Simon.
Sim?
Yeah, I have a question now if you want. So you kind of like remove the noise in the observation space in your parameterization at some point.
Mhm.
If we want also to include a noise model on X, does it change anything into your results?
Yes, yes. No, this is very important, right? So I've assumed away that problem, uh, which is basically I'm saying assume that the model is such that if the observational distributions match, then the F push forward PZ match. And this is basically just, is it possible to do deconvolution? So any noise that you could, in theory, deconvolve. So this is like most additive noises, and I think probably some certain multiplicative noises. I haven't actually thought too hard about this, but I've sort of assumed the way the problem for now. I'm just assuming that the statistical model is parameterized by the push forward. Otherwise, I don't have much to say. It's sort of I'm missing that injectivity from observation to the parameters. There it sort of goes one way, but it doesn't. I don't have the inverse relation. So there's actually not much that I can say about that, except for I think there have been recent results on it's possible to do deconvolution with the additive noise model, even with unknown noise distribution. I believe there was an analyst paper recently about that. But other than that, no, I can't actually say much about that case.
Thank you.
Okay, thanks for your question. Okay. All right. I will get into, oh, yeah, go ahead, Kartik.
Just to follow up on that, so you said in the additive noise model, you could deconvolve even without the noise knowledge, but then what paper is that? Sorry, I don't know. Oh.
It's identifiability of, I'll look for it slightly after.
I mean,
It
I was
was
just curious
used.
because in standard results, usually it's known noise, right?
It's so
The way
additive noise, if it's fully supported, can definitely be deconvolved. You can do this just with like you can show this just with the densities. So like for example, in IVAE, sort of the first step of that proof for linear identifiability is just the deconvolution of the noise.
But you
And
need
it's
to know the
essentially
variance,
it's a
right?
sorry.
You need to know the variance of the.
Yeah. That one. Well, I don't think so. If it's fully supported and the density is strictly positive, you can just push it through the integral, and you can show that if the distributions are equal, then you basically just like do p epsilon of x minus f of z, and then eventually you can get to the point where where px or sorry p theta is equal if and only if uh, f push forward pz are equal. I'm pretty sure that's true, but I'll double check. I think this is in. I think I have an argument for this. I will double check and show you
Okay.
later. Okay.
Simone, wasn't something like this in Seb's paper with an argument similar to that?
That we didn't know the noise? Could be.
I thought there was an unknown noise section at like in the sort of last part of the appendix on the mechanisms, the sparse mechanisms paper, but
You might be right.
maybe I'm misremembering.
It's a long paper.
Yeah.
Maybe before we proceed, can I just ask the organizers if there is a place to like a Slack channel or something to share resources and whatnot after the fact?
There is not yet, but we can certainly accommodate that. We can facilitate that.
Okay, awesome. Okay. All right, okay. I'm gonna continue for now. Almost done, so we'll have some time to discuss after as well. Okay, I'm gonna conclude with a brief discussion on strong identifiability. So recall very early on, I defined strong identifiability as the injectivity of this map from the parameter to the distributions. In a generative model, we can rewrite that right-hand side as the indeterminacy A being the identity function. But as I mentioned, strong identifiability in ICA actually refers to this like permutation and scaling thing. So I've always wondered sort of why is this the case? And is it because strong identifiability, as I've defined it up there, is just completely hopeless to achieve, or is it because of something else? Well, so strong identifiability is not at all unachievable, although if you think about it practically, perhaps it is, but at least in theory, it's not. So let's take a factor model where the loading matrix is lower diagonal and strictly positive on the diagonal. And although I'll note that this assumes that we directly observe a noisy scaled version of the first latent, so it might not be so realistic. We can perform a pretty quick analysis. Triangularity implies that the indeterminacy is also a triangular matrix. And the Gaussian latent implies that the indeterminacy has to be orthogonal. But triangular orthogonal matrices must be diagonal with entries plus minus one, which then by positivity of the diagonal means that it has to be the identity matrix. And hence the model is strongly identifiable. And incredibly, this type of thing doesn't rely on Gaussianity or linearity. And in fact, any triangular monotonic map with a fixed latent distribution is strongly identifiable in this sense. And if you want a reference for that, that's theorem 5.1 in our paper, which I have a screenshot of in the last slide. But again, I'll post that on whatever shared thing that we have. Although I'll mention one thing here. In this case, this is sort of assuming like the exactly complete ICA setting where you have the latent being the same dimension as the observation. So it's more like let's say like a flow model or factor model or like this old school ICA type model. I do wonder if there's a way to extend this by just using manifold structure, but I don't actually have anything to say about that, so I'm not going to try. Here's another example. So recall our result with the multiple fixed Gaussians and how the indeterminacy was just in the orthogonal complement of the span. Well, this means that if the set of means happens to be spanning the latent space, whatever space that is, or whatever Euclidean space that is, the orthogonal complement is going to be trivial, and thus any generative model where you're able to fix multiple Gaussian latents and know their mean is strongly identifiable. So I mean that's a lot to ask for, but so here's my take on why strong identifiability, despite those two examples, were considered impossible in ICA but not factor type models. Well, for one, the blind source separation task that it initially sought to solve suggested that permutation and scaling were simply unavoidable. But more abstractly, in this setting, one might think that the difference between a factor model type thing and an ICA type thing was that while the former assumes a fixed Gaussian, the latter literally allows anything that's independent that isn't a Gaussian. You might think that this is the sort of main difference. But as we've just to make the connection back to the result to our result, the more significant difference is that actually that factor models fix their P of Z while linear IC doesn't, right? And what that means is when P of Z is fixed, the indeterminacies are measure preserving or automorphisms of the latent space. While when P of Z is not fixed, the indeterminacies happen to be measured transporting or isomorphisms within the space of possible latent distributions currently P of Z. And so in the first case, strong identifiability is unlikely, but it's at least possible, right? So we have a blueprint for how we might want to achieve it in this case, which is to reduce the indeterminacies to only include the identity map, which is always measure preserving. In the second case, where you have many latent distributions possible, it's nearly impossible, right? And this is for the same reason why inverse CDF sampling works. It's because of that of the isomorphism theorem of standard probability spaces. A constructive version of this is the Darmot transform, which we commonly seen in these sort of impossibility results of identifiability. Okay, so that's all I have to say about strong identifiability. I'll just end with sort of some forward-looking notes. Fixing the latent distribution is highly restrictive, and while I believe strong identifiability can be realistic for situations in CRL with strong priors or metadata that can inform where the latent means should be, it's probably not realistic for most settings. But at the same time, weak identifiability is vague, right? Which ones are useful? Is linear, or is component-wise nonlinearities? A systematic approach might be to ask for strong identifiability of a task on the latent space, which I've just written here as sort of an invariance of this task function T to the indeterminacies. So for example, linear identification is sufficient for classification with linear heads. I think this is shown in that ice beam paper by Baron et al. Probably not the first author, but anyways. And I think this is particularly important for causal representation learning going forward, right? So here are some possible examples of causal tasks in latent space. Causal discovery, at least with independence tests, is insensitive to the ICA type indeterminacy of permutation and element-wise nonlinearities. Some people might refer to this as disentanglement. Since these transformations don't change the conditional independencies in the latent space. And also the permutation indeterminacy is kind of a funny one, because you sort of like recover the same graph in the latent space no matter what the ordering of those nodes were. So in some sense, the permutation indeterminacy in any identifiability result can sort of be safely ignored, because it's sort of like nothing to tie that down anyways. And similarly, we might ask for these element-wise nonlinearities to be monotonic, and that will preserve a sort of like up-down regulations, say if you're inferring like a latent gene regulatory network or something. And that's sort of all I have to say about that. I think that's going to be nice for, I think I'll talk a little bit more about how task identifiability can be used as a dual concept for more identifiability in the next slide. But for now, my concluding thoughts are identifiability in generative models is an important, and I hope I've shown surprisingly tractable, even in deep models, a theoretical problem, and they have a very, very long history. And there's a lot of nice unifying structure captured by the statistical framework, which I hope will sort of bring more stuff together, bring more work together, as the organizers have mentioned, as a sort of a core mission of the rating group. And two things that I will mention, which I had thought were sort of more important limitations than the observational noise, but this is my opinion, is that injectivity, aka inverting F inverse, does a lot of theoretical heavy lifting. So what happens when the ground truth model isn't injective, right? So actually everything that I've talked about, almost everything breaks if we don't have injectivity. Brian Aragon has a paper with the mixture of Gaussians one. I think it's called Identifiability of Deep Generative Models Without Auxiliary Information, where they relax injectivity, but it's sort of in a very technical sense, where it's like sort of almost injective, like up to measure zero injectivity. But I mean, I think it's a good starting point for relaxing this assumption. But anyways, I don't have much else to say there. And then another thing is identifiability results are asymptotic by nature. What does practical identifiability look like? If we look, there are papers. If you search for practical identifiability on Google Scholar, you will get a lot of like application papers and the medical sciences and whatnot. But I mean, I think this is something that we should also look at, despite having like sort of immense data scale and whatever these days, especially for scientific problems where you might not necessarily have so much data. Okay, and then finally, I left out a couple of things sort of deliberately. One of those things is specific model designs for identifiability, but I'll just sort of shout out some recent examples here, which is obtaining stronger identifiability by actually requiring the representations to perform certain tasks. So sort of adding like a maximum likelihood, a type of regularization to say your autoencoder or something else. For example, requiring it to optimally predict an observed label that might be a function of your latents, which is another assumption that you can make. Is sort of like another example of having auxiliary information in a way that isn't multiple environments. And another thing is there's been several works on sort of interventional causal representation learning without parametric assumptions. So the results that I was able to derive all sort of centered on having multiple exponential family distributions. And now you sort of have these like more non-parametric, I just have single node interventions, or I have some structure on the interventions, and I assume a latent causal graph that can also get a linear identification or something similar. And there are many, many, many other things. And my hope is that these will be discussed in the coming weeks, and just that my talk serves as a useful introduction. And finally, that's it. I'll just say this talk was adapted from ideas presented in this ASS 2023 paper, written with my supervisor, I'm ready. You all know what I look like, so it's a picture of him. And yeah, that's it.
Great talk. Thank you, Johnny.
Thank you so much, Johnny. That was fantastic.
Yeah, if we already have one question in the chat. Divya, do you want to start us off with a question? Or do you want us to read that out?
Yeah, so maybe I did not follow that part on the causal discovery thing. So if let's say I have this permutation error, so the topological order will change, right? So why will the structure that I will learn in the, let's say why will the structure be same in both the bases?
Yeah, so it's just a relabeling. So like imagine like I'm talking about, say, I don't know, smoking causing lung cancer or something like this, right? And smoking just happens to be X1 and lung cancer just happens to be X2, right? Like the semantic information hasn't changed. But if I flip X2 and X1, like let's say X2 now is smoking and X1 is now lung cancer. But technically, topological order, like semantically, hasn't changed, right? It's just a relabeling of it's just relabeling. So you get the same graph in the end.
Yeah, but then how would you compare these two? Let's say like if I have two graphs and I think like if I can relabel the nodes in a certain way, then I'll have the same graph. So do I have to search over different permutations to compute, let's say my F1 score or whatever way I will measure, let's say, the two structures, right?
Yeah, so yeah, I guess this is a fair point. So let's say if I knew the ground truth, then yes, this would be a problem. But I think the point that I was trying to get at was with the latent space, you'd never actually know the ground truth. So sort of whatever structure that you learn is just that structure. And like I can never know that X1 actually was smoking and X2 actually was lung cancer. So it's sort of as long as I see that arrow pointing in the right way, then in essence I'm saying that I've learned latent causal structure. It's just like whether or not you have. So this is also related to that triangular thing, right? Like I said, if you have like assuming a triangular factor model or assuming a triangular model in general basically means that you know which one the first latent factor is, and that's a lot. That's sort of a big assumption to make. But I'm saying without making any assumptions, it's sort of like the best you can do, and the permutation is really something that's unavoidable.
Yeah, thanks for the clarification.
Yeah.
I was just wondering if you have some thoughts on when maybe scale indeterminacy could hurt us. Like even for effect estimation, I feel like if we're always defining causal effects as taking contrast, then maybe even then scale indeterminacy doesn't really hurt. You can always like take your contrast in a different way. But I don't know if you've kind of given more thought to one task or one example where that kind of indeterminacy actually is bad.
Well, so I'll say you're right. Like effect estimation, so scale is monotonic, so at least you'll still see that it's, for example, upregulation or downregulation. If it's all the same scale applied to each of the dimensions, then obviously that's no big deal. You can just sort of mod that out by normalizing. Actually, I'm wondering if you can do the same even if it was different scales. I mean, if it's different scales, then and we can still do that, then obviously we can just mod that out by normalizing and start no problem. But otherwise, I would put that just sort of in the class of the monotonic transformations, where maybe you can't do exact estimation, but you can at least get the sign.
Cool.
Yeah, I guess one thing that I'm interested in with those kinds of indeterminacies is like you could rule those out by just saying I fix beforehand that every latent variable has unit variance or something. So that pins down the scaling. And do you want to do it that way, or do you want to like leave it and then like normalize after? And I feel like these becomes kind of practical questions I think people in the kind of like equivariant invariant deep learning space have thought about a little bit, but not fully answered.
Yeah, I think those are more or less like the same thing. I mean, practical issues, I think there's a lot of work to be done. Yeah.
Maybe could we get one or two more questions? Luigi?
Hi, maybe I can. So I will ask, thanks for the great talk. I wanted to ask your thoughts about, basically model misspecification. So if I understood correctly, you introduced the Identifiability framework in which we have a model class, and then there's two models from this model class. And typically, many times we say, well, one of them is a ground truth, and the other one is the one we learn and we want to. But then my question is what are your thoughts, or whether you know results basically when, let's say, the ground truth is maybe outside, maybe slightly outside for some definition, close to the model class, and what we can say in that case, basically.
Yeah, absolutely. Yeah, this is again a problem that I've assumed away. I think it's a very difficult problem to tackle at this level of generality. I think it's something that probably depends on the specific model class. I guess one thing that I can say is, I mean, if you can sort of define a projection onto your model that is unique, then your identifiability should carry from that projection being unique, right? But if you can sort of have two different observational distributions that each get projected to the same space on your model class, then even if you have identifiability there, you kind of lose that. And I wonder if this is something that we can something to work on, because I think that's a really important practical problem. And I mean, even this like injectivity thing is sort of an example of that, right? Like if our true model isn't objective, then our model is misspecified, no matter how flexible our function class and how flexible our latent distributions are. So I don't have like a really satisfying answer for that. I hope this is something that people will think is important, and I'm glad you think it's important, and we'll work on. But I think maybe the projection thing can go somewhere, but I'm not sure.